Okay, we're ready to go with this last talk on understanding and finding Java decompiler bugs. The talk will be given by Yifei Liu.
Yeah, thank you. Hello, everyone. Today, I'm going to present our research that is understanding and finding Java decompiler bugs. I'm Yifei Liu, and I complete this work with my collaborators. They are Weidong, Minxue Pan, Xuandong Li, and Zhendong Su. And my presentation has the outlines. It has 5 parts. And so first, we have to know what is Java decompilation. That is to convert Java bytecode into high-level Java source code. And there are numerous well-known and frequently used Java decompilers with GUIs. So maybe you know, such as the JD GUIs or JEDEX. And there are usually the Java decompilers embedded in IDEs, such as the IntelliJ IDE, Android Studio, and so on. And if you want, you can have a look at the compiled code of the third-party libraries you used in your projects. And furthermore, Java decompilers often work as one of the foundations of program analysis and frequently used for vulnerability detection, malware detection, and ground truth construction. However, Java decompilation seems simple, but is a non-trivial task, and it is far from satisfactions and contains quite a number of bugs. For instance, such pieces of code, if you write them in the IntelliJ IDE and compiles and decompiles it, you can get the right path side. And here is a duplicate definition of the variable var2, and it is quite confusing the users, and such obvious bugs should be prevented. In this work, we wonder what is the root causes of these bugs and whether we can have any solutions to help developers to improve their Java decompilers. And in our work, we select the 3 most famous Java decompilers, the CFR, FanFlower, and JEDEX. To note, the FanFlower is the official decompiler used in the IntelliJ IDE, and we select 300 unique bugs from them as our study subjects. Each bug contains its own descriptions from the issue reporters and has corresponding commits to fix these bugs. And from both sides, we can therefore have a better understanding of Java decompiler bugs. And here, first from the outward appearance, we analyze the characteristics of the Java decompiler bugs, and including the provided artifacts. The artifacts are those that the issuers provided to the developers so that they can reproduce and locate the bugs. And then we have 5 kinds of the artifacts, including the source code, the decompiled code, and executable artifacts, possible fix, and the error symptoms, error positions. And we hear the table and the figure listed their distributions. And the 276, that is over 80% of bugs, provide at least one of source code, the compiled code, and the executable artifacts. Furthermore, we have a further investigation of the 80% of bugs, and we found that half of them are from the real-world applications, and 40% of them are in the form of small test examples. Maybe they are potentially written by the issuers themselves. And this finding implies us that small test examples can also be used to help reveal bugs in Java decompilers. And the real-world programs are not always required. It is the first finding in our study. And now let's move to the second characteristics of bugs, that is the error symptoms. That is how the bugs manifest so that the developers or the issuers think they are real bugs in Java decomplilers. And we have 6 kinds of bugs, such as the exceptions, syntactic, semantic, configuration, and GUI errors, and the performance issues. And here, the top 3 are exceptions and the syntactic and semantic errors. They account for almost 80% of bugs. And here we can have a look at the semantic errors that they account for over 20% of the bugs. Why we pay special attention to these semantic errors? Because semantic errors are quite dangerous, and if we don't have the source code, we are difficult to review these bugs. Suppose there's an industrial app that is a malware, and we don't have its source code, but the Java decompilers tells generate the incorrect code and indicates that it is a good one. Then this malware may bypass the security check and do anything harm, and it can do anything harm while we are unnoticed of these harmful operations due to the incorrect decompilation. And this would and it is a great challenge and poses to the security, and we should take care of these semantic errors. It is the second finding in our study. And the last characters of the bugs are the fixing duration. That is the time required to fix these bugs. As the figure shows that 80% of bugs in CFR and the JD-Testerutilizes, the two compilers, was fixed within 15 days, while FanFlower, it takes significantly longer time to fix these bugs. Maybe because it has more strict bug checking mechanisms in their bug issue trackers. And here's the general characteristics of Java decompiler bugs. Now let's talk about the potential causes of these unique bugs. And here we give some interesting cases so that we can they are founded in the fixing commit of these bugs. And the first kind of these cases is related to the sugaring, or we name them as sugar S. And for specific Java source code structures such as the lambda expressions, the anomalous classes, they are usually compiled into multiple Java bytecode instructions in specific manners. For instance, for the lambda expressions here, it is first compiled into the synthetic lambda method, and then this method is invoked according to the meta factory invocation. And certainly, in the decompilation, the compilers can generate the code that exactly mirrors the bytecode, but it is usually difficult to understand. So they usually prefer to translate them back into the lambda expression, and that is sugaring. And the bugs can easily fail in the corner cases of this sugaring process. For instance, the out-of-package invocations for lambda expressions, the sugaring for nested lambda expressions, and so on. The second kinds of the cases are related to region restoration, and we name it as the case R. Many high-level construction flow structures in Java are usually compiled into several instructions, such as the goto. For instance, the if or switch and the breaks, they can translate it into one or several jumping instructions, such as goto. And here we name as the goto structures. And the challenges may lie here because for instance, each goto into a goto structure may be mapped to different various goto structures. So it is error and try process to select the most compatible goto structures. And the challenges may be more tough when under different compilation environments or under the different combinations of goto structures. Now here's a lot of bugs related to the region restoration in the CFR and the JD-Testerutilizes. And the last kind of the cases are related to type inference, and we name them at the case T. Case T has two parts. The first part is related to the generic types. As we know that the type parameters of generic types, especially those of local variables, are replaced with objects in the bytecode. So in the decompilation, the decompilers should infer which the parameters should be for these generic types according to the data flow associated with these variables, and it is a non-trivial task. We know that, and most of the compilers hasn't fully finished their development of type inference systems, and it also leads to a number of bugs related to type inference. And another part of the type of case T is related to the indistinguishable types. That is, in the bytecode, many values of types, for instance, the type int and byte, can be intermingled in the bytecode. And it requires the compilers to carefully determine whether a value should be classified as an int or byte. For instance, here, the variable b here, it is an int in the source code, but in the bytecode, it can be used as both int and byte. And even the I2B instruction even indicates that this value can be a byte. However, if you indeed treat the variable b into a byte, it will lead to a semantic error. As here, the output b, the invocation, it may lead to the invocation of the method below, not above one, and it is a semantic error and quite dangerous. It is a third finding that these three kinds of cases poses most challenges in our Java decompilation, and the developers should be cautious when handling them. And there are further informations regarding the causes of these unique bugs, including the details about the buggy files, the modified lines of code, but due to the time constraint, I can't cover them all here, and you can refer to our paper and for more details, and they are all public available with our all artifacts. And that is all of our study. And this study indicates that there are still quite a number of challenges and bugs in Java decompilation. And how can we help developers review these bugs? Testing. It is the most frequently used and effective methods. And how can we test Java decompilers? According to the findings in our study, we can utilize the advancement in Java decompiler testing approaches. We can use their test generators to generate high-quality test cases, though they are designed for the Java compilers, but they can also be used to test the Java decompilers. And second, we also take the strategy of differential testing so that we want to check the decompiled code and the source code, whether they are both syntactically correct and semantically equivalent. And at last, we should carefully select our test generators. Here we select the Java father and the Yifei test. There are two SOTA Java test generators available from both industrial and academic. And they can generate various combinations of go-to structures, lambda expressions, indistinguishable types, and generic types. We think with these two generators, we can help developers to review the bugs related to the three cases summarized in our study. And that is our JD-Tester, differential testing framework for Java decompilers. And the JD-Tester follows a workflow of compilation, decompilation, recompilation, execution, and reduction. It collects three kinds of failures, including the exceptions thrown in the decompilation, the semantic errors reported in the recompilation, and the comparison results, indicating that the generated code and the decompiled code present different semantics. We also conduct experiments on our JD-Tester, and we select the three studied Java decompilers as our test object. And we use the 1,160 test cases generated by Java father and Yifei test as our test subjects. And here, the two figures shows the failure rates. On the left one, it shows the result on the tests from Java fathers, And here we can see that Fanflower is the most reliable one, and it only failed on 66% of the cases, while CFR and JDX failed on 36 and even 84% of the cases. While on the right, that is on the test from the Heffer's test, the 3 decompilers show comparable failures rates ranging from 40% to 60%. And most of these bugs are recompilation failures. And here we listed the detailed data of these failures and the corresponding bugs revealed from them. Here, the possible explanation for the extremely high failure rates may be that the 3 decompilers may frequently repeatedly failed on similar code patterns. And an interesting finding is that Fanflower shows superior performance on the tests generated by Java Father. It may be due to it uses a Taijong's algorithm in region restoration, and so that Fanflower get rid of the most region restoration failures than the other 2 compilers. From these failures, we manually checked this result and revealed the 62 decompilation bugs, and we reported them for the first time on almost all the bugs. And we listed them all here, and we found that they are, most of these bugs are related to the 3 cases, that is case S, case R, and the case T, summarized in our study. And they are also publicly available for further analysis. Moreover, around 15 of the bugs are related to semantic errors. As we have mentioned, they have no obvious outward error symptoms and are usually difficult to be reviewed without source code. And the 13 bugs reported to the developers has been fixed or confirmed. To conclude, in this work, we conduct an in-depth analysis of Java decompiler bugs from both terms of their outward manifestation and their root causes. According to our study, we propose our JD tester, the differential testing framework targeting Java decompilers. Our experiments results show that our JD tester detects 62 real-world bugs in the 3 most famous Java decompilers, and 13 of them have been fixed or confirmed. Thank you. That's all. Any questions?
I think we might have time for maybe one question. Okay, I'll ask one of my questions. So you mentioned this motivation of malware, right? And the idea that if you have a semantic issue in your decompiler, that you might misunderstand. But if I were a malware author, I might try to generate bytecodes that don't even map to Java source code, right? So I might not start with Java source code because the Java virtual machine can express programs that cannot be written in Java source code. So did you think about those cases at all? Or were you focusing only on Java bytecodes that could originate from the Java compiler?
I think first that Java compilers that do its optimization into the JIT. Yes. I think. Would you please repeat your question?
So, for example, if I write my code in Scala, I can get Java bytecodes, and I wouldn't expect these tools to be able to decompile that back to Java code. So my question is, did you focus entirely on bytecodes that can come from the Java C compiler, or did you look at other types of bytecodes as well?
In fact, all our algorithms can be used on all languages, and for instance, the Scala and the Kotlin and many other languages, they can use all their bytecode can be transformed to the Java bytecode, and that is a promising process. I think they can also benefit from our work. Yeah.
Okay. Thank you.
Thanks.
Any other questions? Okay. Oh, okay. We can do one more question.
Great talk. Very interesting topic. Have you also considered comparing the generated bytecode of compiling the decompiled source? So, like, one thing is just comparing them on source level or comparing them on running them, but actually comparing directly on the bytecode. I don't know if you got that.
Pardon, please. I didn't hear clear. Do you mean that we compare and decompile and recompile the result and have a comparison that?
Yes. So.
Yeah.
The actual bytecodes that come out.
Yes. Several previous work has compared the bytecode, but there's problem that maybe that the bytecode, though they are unlike, but they have the equivalent semantics. That is difficult to check. Yeah, so that we use the test as a semantic equivalence check, but not focus only on the similarity, maybe or the equivalence of the bytecode. Yeah, it's a very interesting, very important question. Yeah, thank you.
Okay, let's thank the speaker again.